Okay, we're going to do three equations and three variables today. Section 3.4. I've got just a couple of short notes and then we'll do three examples together. Um, so it's three equations and three variables, which if you think back to all of the stuff that we've solved so far, we started if you had one variable you would only need one equation. So if I had this, very easy to solve, one variable, one equation. Then we picked up systems of equations, which was two variables. And if we have two variables, we needed um, two equations, and we solved using elimination or substitution, or we graphed. And now we're on to three equations and three variables. So you instead of an xy coordinate, you have an xyz coordinate, or sometimes we use ABC, or they just like you to write them in alphabetical order. Graphing is done on a three-dimensional plane, so you have an x and a y, and then you have a z. You have to picture my pen going directly through that. It's hard to draw on here. If we have that coming out the back, and then when we graph it, we go x, y, and then there's depth. So um, we can talk more about the 3D when I get back. Solutions are either one solution, no solution, or infinitely many solutions. Let's take a look at one of each of those. When we have one solution, the three individual planes intersect at a specific point. There is one point where they all cross over. If you think about where the front wall meets the side wall meets the ceiling, you have a single point on the front wall, the side wall, and the ceiling. That would be one solution. Infinitely many solutions, that could be just like when we had two equations and two variables. If all three of them are the same plane, if they're all the same, then there's infinitely many. But also if we have three of them intersecting at a line. So if you look at again where two walls intersect, the corner of the two walls is actually a line going up and down. And then if you sent another one, so if we had this green was a wall and this yellow was a wall, there's the intersection, and then we put the blue one through there. That line means infinitely many. Um, and then you could have no solution where no points in common with the three planes. Um, it could look like this, where there's an enclosed space. It could look two parallel and then one going through them. These two don't have any in common, and then of course we have three parallel. Um, but just like with two equations and two solutions, all you're looking for is this one will come down to, you'll have an x value, a y value, and a z value. Infinitely many solutions, you'll get something that's true. Again, you'll get something like 0 equals 0. Since that's true, there's infinitely many. And then over here you'll get something that's false. You'll get 0 equals 12 or something like that. We saw those with two equations and two variables. Okay, so here's our first example, and we do have a couple of steps that go along with this. The first thing I like to do is name this equation number 1, equation number 2, and equation number 3. Because the first step is going to be combining any two of them to eliminate one variable. So 1 will be combine two equations to eliminate. So we're going to use elimination here a lot, a variable. I'm going to do that by, I look at this and I see z and negative z. So I'm going to do 2 plus 3. And I like to rewrite them. I know some of you won't like that, but when we get into multiplying, you're going to want to rewrite them. And when I put them together, I get a new equation, which is 2x minus y equals negative 4. Step 2, we must use the other equation and we will again combine to eliminate the same variable. So in my example, I have to use equation 1 and I have to get rid of the z's. Because what we're trying to do here is to create a system of two equations and two variables, which we just spent 2 sections solving. So I'm going to go and I'm going to do 1 and 2, but I'm going to multiply equation 2 by what? If you said 3, you're winning. So equation 1 is 2x plus 3y minus 3z equals 16. And then now the new equation 2, I can multiply everything. And don't forget to multiply what's on the right. And now when I combine these, I get 5x plus 6y equals 7. So now I'm going to use these two equations and I'm going to solve using those two. I will be able to get x and y. So I'm going to take my new two equations, let's call it equation 4 and equation 5. You don't have to. I'm going to put 4 and 5 together, and I'm going to multiply equation 4 by 6. So if I do this whole thing times 6, I get 12x minus 6y equals negative 24, and I'm going to combine that together with 5x plus 6y equals 7. And now I will have 17x equals, wait for it, negative 17. X equals negative 1. Once I get x equals negative 1, you work your way backwards. I would put this negative 1, I can put it right in here and solve. I guess I would probably put it into this equation 4, and I get 2 times negative 1, which is negative 2, minus y is negative 4, and then I would get plus 2 plus 2. Negative y equals negative 2, or y equals 2. And I'll put that back up into number 2, I would say. X plus y plus z is negative 3. So I'll have x plus y plus z equals negative 3, which is 1 plus z equals negative 3, which is z equals negative 4. My answer is in the form of x, y, z. Check your work, plug it in. I'll let you do that. Enjoy. Next one. This one either will have infinitely many or no solutions. So the first one was an example of one solution. So I look at this one and I think to myself, hey, looky there. I got a y and a negative 3y, and then I got a y and a... So let's multiply equation 1. Oh, I didn't label my equations. 1, 2, 3. I'm going to multiply equation 1 by 3, and I go over here and I do 1 and 2, and I take good notes, and I go 3x plus 3y minus 6z equals, whoops, I forgot my niner. Did somebody say niner? And then I got negative 3x minus 3y plus 6z is negative 9. And I get 0, 0, 0. Oh my gosh, 0 equals 0. When is 0 equals 0? infinitely many solutions. Infinitely many solutions. Now, we could go a step further and combine these two and figure out what is the equation of the line that makes it work. I'm not concerned. I just want you to be able to identify infinitely many solutions or no solutions. So you can already see if this was a no solution problem, maybe this -9 was -12 instead. So I would get 0 equals -3. There you got a no solution and you move on. And of course we have word problems. So the school store sells pens, pencils, and paper. Pens are $1.25 each, pencils are 50 cents each, and paper is $2 per pack. Yesterday the store sold 25 items and earned $32. Number of pens sold equal the number of pencils sold plus the number of packs of paper sold minus 5. How many of each item did the store sell? Well, let's use P for pens, P for pencils, and P for paper, and then get the problem all wrong. How about X for pens, Y for pencils, and Z for paper? So we should identify our variables, define your variables. So I know I have X plus Y plus Z. How many total items? 25. And then we'll have money, $1.25 per pen plus 50 cents per pencil plus $2 for paper. That's a 0.5 there, and that's a 5, even though it doesn't look like it. Equals $32. So money plus money equals money, total number plus total number equals total number. And finally it says the number of pens sold equals the number of pencils equal the number of pencils sold plus the number of packs of paper sold minus 5. So I've written my three equations after defining my variables. If I was doing this, I would probably go ahead and say, let's turn this one into standard form. X minus Y minus Z equals -5. So I got equation 1, equation 2, and then one of these is equation 3. I'm going to go ahead and combine 1 and 2 because it looks like the y's will go away. So I'm going to do, 1 and 3. 1 and 3. I'm going to use the 3 right here just because it's sitting there. X plus Y plus Z equals 25. Lo and behold, X plus X is 2X. Y's go away, Z's go away, equals 20. Well, isn't that great? X equals 10. 10 pence were sold. Next, we can put the 10 up into my equation for number 1 and 2 because I did 1 and 3, so I can plug it into both of them, and then I'll be able to solve for the other one. So I'm going to put it into equation number 1. So I have a new equation that'll say 10 plus Y plus Z equals 25, which will be Y plus Z equals 15. So there's my equation number 4, so to speak. My next one that I can use, and then I could put it into equation 2 there, and I get 125 times 10 is 12.5 plus a half of Y plus 2Z equals 32. Subtract 12.5 from both sides, I get a half of Y, and I get plus 2Z, and I get 1950, if I remember correctly, 19.5. So there's my equation number 5. And now I can put 4 and 5 together, and I'm going to multiply this guy by -2, because I can get rid of the z's then. So I get -2y minus 2z equals -30. And I have, a half minus 2, that's -1.5. Z's go away, equals 10.5. -10.5. Very important. You can't have a negative number of packs of paper, right? Divide by -1.5. Divide by -1.5. Oh, where did my y go? Oh, this is pencils. Pencils. Y equals 10.5 divided by 1.5. I believe that's 7. Please check my math. And lastly, Z would have to be, well, I got 10 packs of paper. I got 7 pencils. That's 17. Plus what is 25? Must be 8. So I've got myself 10 pens, 7 pencils, and 8 paper. Boom. We are good to go. So there are 3 examples. And now you can always play this back if you would like to take a look at those examples again. Hopefully I didn't make any mistakes. Of course, if I did, it probably would be my first one of the year. Have a lovely day.